Just a setup. I'm actually a little bit ahead of the game. The lab we're going to do on Thursday is the mystery powders lab. Now we have 3 people who are going to be gone for that. So are you part of the gymnastics as well? Yeah, okay. Just making sure. I think it was Vanessa that talked to me. It was Brandon. What's your? You're not? Are you lying?
I am not lying. I am just not telling the truth.
Okay, just prevaricating. Okay, so if you've missed labs, you do need to make them up. There's no drop labs, so the people who are going to be gone, if you can come and take it Wednesday, that way you get it done before you go. If not, we'll have to do it later because I got to get chemicals and stuff from chemistry. I'd rather do it Wednesday afternoon if you can. But if the 3 of you can't do it, then we can't. So let me know when you'll be doing it so I can be ready because I have to get all the chemicals and stuff. Now, this lab, before you come to lab, and I know you have 3 days of preparation, there is something you have to do. This part right here. It should be done before. Here, let me put it in highlighter or not. Apparently, I can't highlight this document because I scanned it and it doesn't know that that's text. Okay. Well, you have to do this part before you can do the experiment. And so I recommend that you do it before coming to class just to save yourself some time. So what is that part? What we have is a set of 1, 2, 3, 4, 5, 6, 7 tests. And you don't have to do all 7 tests for every chemical. Because if you look at the test, here's the outcomes of the tests for the different chemicals we're using. So as you can see, the solubility test, the ones above that line are insoluble when you put them in water. That is, they won't dissolve. The boric acid you'll have to be careful with because it's moderately soluble. But that's the first one you should do because that's going to subdivide about 50-50, right? So you want to get that 50 out of the way first. And then you want to say, okay, let's say that, for the ones that are insoluble, this test has 1 that's positive and 2 that are negative. This one has 1 that's positive and 2 that are negative. So you have to do both tests. Well, if you do this test and it's positive, you know it's cornstarch. If you do this test and it's positive, you know it's white chalk. And if you do both tests and it's negative, you know it's the third, right? These down here, notice this has 2 things that react different than the rest. This has the same 2 things that react different than the rest. This has 1 that's different than the rest. This one has 2 that are slightly different. And then this one here has 4 that are insoluble and 2 that are different. So you need to go through and figure out now what test order can I do to have the fewest likely tests. If you look at this, test 3 and test 4, what stands out about those 2 tests?
Mostly negative.
Not just that they're mostly negative. What are you going to find out from one test compared to the other?
Color.
Well, in terms of which material it is. This chemical responds to both tests. This one responds to both tests. All the rest don't. Those 2 tests are redundant. If you do one, you don't need to do the other because they have the same separating ability. So when you go through, I would not say, I'm going to do test 4 and then test 3 because if you do test 4, there's no point in doing test 3. I chose test 4 because it has clear positive and negative as opposed to light pink and medium pink. Right. So when you go through and you're making your flow chart, And a sample flow chart that's incomplete is shown here. And it doesn't tell you exactly what you're going to do. It's just, laying out so you know what you're going to do. So you should make yourself a flow chart and just put that flow chart here. So you're going to first do this test, and then if it is condition A, then you're going to have, it has to be one of these chemicals. And if it's condition B, it's got to be one of these chemicals. And then on these chemicals, you're going to do this test. And if you get this outcome, it's that. And if you get this outcome, it's that. And write down which test you're going to do and which chemicals flow through. So at the end, all you have to do is start with a chemical, and you do first your water soluble test. And then depending on the outcome, you either do this one or this one. If it's here, depending on the outcome, you either do this one or this one until you know exactly which chemical it is. So that's the thing you want to do before coming to class, to lab on Thursday, is have that flow diagram figured out, the order you're going to do the tests. And what we're going to be testing is both some chemical reactions and some just physical states. And so one of your questions is which ones are testing which. Did you have a question, Carmen? No. Okay. I thought. Okay. So everybody understand about the lab?
So are we testing everything? Like, I'm confused on why we have to make a flow chart before.
Okay. You are trying to do the minimum number of tests possible, right? The goal is to get out quickly, but to do it right. And so you want to have that flow chart. So for some elements, like if I am going to do the cornstarch, now you don't know which one's cornstarch. They're just going to be labeled 1, 2, 3, 4, 5, 6, 7, whatever. So you don't know which one's the cornstarch beforehand, and it warns you, don't taste it. Some of these things, of course, salt, sugar, you can tell by taste, and historically chemists did that. But some of them are not good to put in your mouth. So that's why you have the don't taste the part, because you don't know until you taste it if it was something you shouldn't have put in your mouth. But let's say that you are doing the cornstarch. If your first test is the water and you find it's insoluble, and your next test is vinegar, and you find that it's negative in the vinegar test, then you're done. Only took 2 tests to identify that. But if your order is test 1, and then if it's insoluble, going to test 4, then if you do cornstarch, you'll have to do both 4 and then 2. And if you do plaster Paris, you'll have to do 4. Truth is, it doesn't matter if you do 4 first or 2 first. But you'll have one that you only have to do 2 tests on. Brittany?
So are we testing everything then, or are we just picking one of them?
You're going to be testing all of the chemicals, but only doing the number of tests necessary to determine which chemical it is. Or not chemical, but powders.
So we should have multiple flow charts, is that what you're saying?
No, you have one flow chart that says, I do this test. If I have this outcome, then I know it's one of these different powders, and then I'm next going to do this test. And if I have this outcome, then I know it's just down to these 3 powders, and I'm going to do this test. And so you have a flow chart that tells you, okay, what test do I need to do next until you know exactly which powder it is.
What is this one called again?
Mystery solution, I believe. No, mystery powders. Instead of mysterious powers or something, I think. Because these are all funny, You figured that out by now, right? Okay. So today we're looking at chapter 15, I think, how atoms bond and molecules attract. So we're going to learn here some actual chemistry type stuff, So first we're going to learn about electron dot structures. How many people know about electron dot structures? Just to see what people know beforehand. So only 2, okay, 3. So this is mostly new to people. So atoms bond because of electrons. It's not the nuclei that make them bond, it's the electrons. That's why for chemistry purposes, it doesn't matter which isotope you have of an element. If I have carbon 12 or carbon 13 or carbon 14, it still has the same number of protons in the nucleus, which means its electrons are going to have the same energy levels and the same number of electrons, and so it's going to behave chemically the same because the electrons are the same. Doesn't matter how many neutrons you have because that's not going to affect the electrons. So the protons aren't involved in the bonding, but they're involved with setting the energy levels of the electrons that do the bonding. So it's the electrons that are doing the bonding. And so when we have electrons doing the bonding, the electrons, we talked about the shell structure. The electrons that are close to the nucleus that are in the lowest energy states, those aren't going to do any bonding. It's only the ones that are the most loosely held that are going to be involved in bonds. And so when we look at the electron dot structures, we're only going to look at electrons that are most loosely bound. So let's get to, well, the electron dot structure is based on the shell thing that I showed you before. And I talked about a little bit of, they're lying to you here to make it convenient. It's important to note, a conceptual model. It's not reality. It's not what it looks like. Remember, the electrons, we don't know where they are, but I showed you pictures that showed where we're likely to find electrons, and in some atoms, it's nowhere close to spherically symmetric. But this helps us to understand and visualize how things will happen. So the goal is, this model is telling us how things are going to behave. So it's not a truthful model, it's telling us how things are going to behave. So the dot structures. We have up here a little periodic table, and we're looking at the top 3 elements in the right-hand column. The right-hand column, what we call the noble gases, are special because you have as many electrons as will fit in the outer shell. If you have as many as will fit, it's really happy. It doesn't do anything. It's inert, chemically inert. Doesn't do anything. And so all of these have a complete outer shell. So helium in the first shell, you can only put 2 electrons there. And so helium has 2 electrons in the first shell, and it's complete. Now, if you go to the next one down, neon has 2 in the first shell and 8 in the second. Once again, if we look in here, it shows 8 for the second and 8 for the third. 18 for the fourth because, well, you have the metals that these 18 is including the electrons that really should have been in this section. Remember, I told you it's not exactly accurate because that's the order they fill. So this has a full 8 for neon in its outer shell, and argon, once again, has a full 8 in its outer shell. So these are inert because they have the full 8. So we have a pair here, a pair here, a pair here, a pair here. Pair here, pair here, pair here, pair here, pair here. Notice I didn't circle the ones that were in anything but the outer shell. It shows us in light electrons that are in closer shells, but I didn't circle those because which electrons can participate in bonding? Only the ones in the outer shell. Question, Brittany.
Are they always in pairs?
That's what we're getting to. If they're in pairs, they're not going to bond. If they're not in pairs, then they will bond. So these are all in pairs, so they won't bond. So if we look at something else like chlorine, where's chlorine in the periodic table here? Brittany just points behind her. It's back there. Other students turn to look. Brittany just knew. Okay, she said she pointed to the right place. Chlorine's inside that box, which puts it in the column that we call the halogens. The halogens, what they all have in common is one less than a filled outer shell. So the chlorine, instead of showing the circle, we just showed the electrons on the outer shell. We didn't show the 2 that were, well, actually, the 10 that were closer than that. We only showed the outer shell. And so we have 2, those are paired, not going to do anything. 2 paired, not going to do anything. 2 paired, not going to do anything. But this 1 unpaired electron, that's something that can participate in a bond. If we look at carbon, carbon has 4 electrons in its outer shell. How do I know this? I can just look back there and count. All right. The first column, 1 in the outer shell. Second column, 2 in the outer shell. If you go to the fourth period where you have scandium, titanium, and so on, those are metals and they're a little bit tricky. So let's just skip over to the column that has boron. Those have 3 in the outer shell. The one with carbon has 4 in the outer shell. So everything in there. So carbon, silicon, germanium, antimony, lead, they all have, no, that's not antimony, that's tin, isn't it? SB is antimony. See how well I know my periodic table. Those all have 4 valence electrons, electrons that can be shared. So we call them valence electrons. They are available for sharing or bonding. If we look at krypton, we didn't look at krypton before. It shows 8 there, right? If you look at that chart, krypton, it's in the 4th row, and it has all of those from scandium to zinc that are not counted in this 8. Those electrons aren't being counted. If we go back to this picture, right, it shows 18 for something that's in that row, but we're only showing the 8 nonetheless. So for most of our work, we're going to ignore those metal things because we're not a high-level chemistry class here. No. Sorry to disappoint. So here you see the electron dot structures for the ones I said we are going to pay attention to. What do we call this column? Column 1 was alkali. And column 2, nice spelling. Column 2 was the alkali earths. And then we come over, I don't know names for those. This one here, the textbook gave us a name that was like the Chalogens or Chalogians or something like that. But we all know, or we all should know, this one is the halogens. Such as we have light bulbs that are halogen light bulbs. The halogen light bulbs have a halogen gas in there that helps to rebuild the filament. And then we have this one here that's the noble gases. So you should know the names for the columns 1, 2, and 17 and 18 as numbered here. Are they numbered the same back there? I can't tell. Yes. Okay, good. Notice the dot structures. Everything in the column 1, how many dots does it have? 1. Column 2? Pretty surprising, isn't it? Skip over to column 13. 3, 14, 15, 5, 16, 6, 17, 7, 18, 2, or 8. So we've got those dots. What did I say they're good for?
Number of electrons in the outermost.
Okay, they tell us the number of available electrons for bonding, and so that's going to help us to understand if something's going to bond or not. So our first clicker question. Sodium, Na, has atomic number of 11. It has only 1 valence electron. If you look back there, sodium is first column, third down, Na, natrium. Upon losing this electron, what other atom in the periodic table does the sodium resemble? That is, its electron structure. So if you take 1 electron away from sodium, what atom would have the same electron structure? tried to look stern. I tried to look stern. Stacy, Jocelyn, and Brandon. It's down to everybody. Okay, we had 11, 1, 3, 2. So we had a pretty clear answer there. Let's go to Jocelyn. Can you explain the situation for us, please?
Wasn't really sure what to put, honestly. I'm the one soul that is on B.
Okay.
I think I confused it with something else, but I was just thinking losing an electron. Something increasing. I don't know if that's right.
Okay. If we start with sodium, it has 11 protons. That's what the atomic number means. But we had a question, one of our clicker questions, I think it was, that was how many, what does the atomic number tell you? It directly tells you the number of protons, but it also tells you indirectly the number of electrons. Because if you have a neutral atom, it's going to have the same number of electrons as it has protons. So that means the sodium atom starts with 11 electrons. If you take away one electron, how many electrons are left? 10. Okay. So if we have 10 electrons, how many protons in the nucleus would normally have 10 electrons? Neon, because neon has atomic number 10. And so it's going to, if you take away an electron from that sodium, it's going to have the same same number of electrons, so the same filling. It's not going to have the same energies, but the same number of electrons filling states as neon. Now, neon, what do we say about neon's chemical reactivity? It's lame, to quote Casey. It's inert. And so if we take that electron away from sodium, then the sodium should be inert, right? Except for one thing. What's the charge of sodium if I take away one of its electrons? It's now going to be positive. It was neutral. We take away an electron, it has one less negative, hence a total positive charge. So it's going to be inert, except it has a positive charge. And so that positive charge what would it do to other positive charges? Repel them. What would it do to negative charges? Attract them. So while its electrons are inert, it has the ability to have what we call an ionic bond, where that charge attracts something with a negative charge. So here's the picture to go with sodium. You take away the one electron. Now this outer shell is empty, which means it's got nothing going on, and the one just inside is completely full. The other side of that coin would be if we were to take something that has one less than a complete shell, like fluorine. If we have fluorine, which has nine protons and thus at neutral would have 9 electrons, and we add an electron to it, then it's once again, each electron is paired, that's low energy, it's all happy, and it's all inert. But now it has one more electron than proton, so it has a negative charge. So if I have sodium that has given up an electron because it's really stable dropping off that electron, and I have fluorine that has added an electron to get to a more stable configuration, how are those two going to interact? Positive and negative. They're going to attract. So those will be pulled together because of their opposite charges. Now, that example I gave you is a strongly ionic bond. Here is a weaker version. You take a hydrogen ion. So you have a hydrogen nucleus, a proton, normally comes with one electron. If you add one electron, it'll have a negative charge and have a complete shell. If you take away one electron, well, it has a positive charge, but once again, it's complete with nothing. And so the hydrogen ions are reasonably common. You have oxygen. What's the net charge of oxygen? Or not oxygen, water. What's the net charge going to be? If I have water come out of the tap, what's the net charge of this water coming out of the tap? Should be neutral. And as we go through this, we'll understand that aspect better. So this is neutral. But oxygen has a dot structure like that. How many unpaired electrons does it have? 2. Why doesn't it have those 2 paired up in an area with, or just 3 sets of 2? Because for stability, when you put the electrons in, they go 1, 1, 1 in all of the available, actually they go, I should be a little clear. The first one in and the second one pair up because they're S. Then the next ones go around separately. Carbon, then when you get to 4, is a little special. There's special rules there. But it's lower energy for the electrons to not be paired up in this case. And so we have those 2 lone electrons. Hydrogen, how many electrons should hydrogen have? 1. So I start like this, and then that hydrogen forms a bond here, and this hydrogen forms a bond here. So now I have an oxygen molecule where I have electrons that are shared between the hydrogen and oxygen. Now this is coming up later. I just wanted to get it here since we have water. So these are shared. If we share electrons, then we call it covalent because it's shared together. If they're not shared, if it's like the sodium and the fluorine where the sodium gave up an electron, the fluorine grabbed that electron, then we call it ionic. So that's how water is formed. We now have a complete, if you go around the oxygen, a complete 8. If you go around each of the hydrogens, you have a complete 2 for the hydrogen. And so each one is now happy because it has the right number of electrons. Now, the water molecule is not, if you look at my picture that I just drew with the dots, you would think that it's just flat with a hydrogen on either side. But the fact is we have 3-dimensional shapes. And so what happens is you have the oxygens are pointing up like this, or excuse me, the hydrogens, if my oxygen is my hand, the hydrogens are up like this. And then the lone pairs are, of course, this and this, are going like that. So they're pointing the opposite direction. So what that means is we have the hydrogens up here that are happy to give up a few electron, or not a few, happy to give up some of their electron. The oxygen that wants more electron. So the oxygen ends up with a net negative charge, and you have the lone pairs below it. So this behaves like it's negative on this side and positive on that side. Is it getting confusing? So if this is negative and that's positive, what are they going to do? Attract. And so we form a hydronium, H3O. That's not a neutral molecule. That's an unusual one because it's an ionic molecule. Ionic meaning it doesn't have a charge of 0. So that's hydronium. Everybody happy? Hydronium? Yay. So the example with sodium and fluorine. What's it going to do? This is a positive charge because it gave up an electron. This is a negative charge because it grabbed the extra electron. What are they going to do? They're going to attract each other. So they're going to come together and form a bond. So sodium, the electron structure, just looking at the outer level, sodium, it had one electron, right? The fluorine, it was missing one electron. When we draw the picture, we'll still take this and just bring it over. But the reality is that it's not sharing those electrons like it looks to be. It's held together because one side's positive, one side's negative, and the electron is almost completely over there with the fluorine. So it's going to form a bond, and we have some different pictures to show. I thought I had the pictures before this question. I hope I didn't remove them, because we had a picture that showed the electrons. Let's just do this question and hope that I didn't take something out by accident. So what is the chemical formula for a compound made of aluminum ions, Al3+, and oxygen ions, O2-? How do you find that out? You do. We want to have a neutral molecule. Oh, crud. I forgot that it shows you that. I have a different slide on the one for the clickers because I want to remind myself that I have a second slide I'm going to. My bad.
The answer C. I mean, but there's still the clicker people who don't have.
That's right.
Yeah. So can you give us the answer?
I want you to think about it. That's their detriment. That's their lack of learning ability.
Ouch. Who's getting extra credit?
Yeah. Okay, so Eric, Hannah, and Jocelyn are still out. All right, everyone has answered now. Oh, come on.
Whoa.
It says no one answered. I mean, it says 17 people answered, but it shows me none.
1 for B and 16 for C.
Does it show you that? Because it doesn't show me that.
Mine says not.
So you said 1 for B and 16 for C? Thanks, because, yeah, like I said, mine is showing me nothing. Okay, let's go to, well, first, how do we do this? We need to balance the charge. So if I have 3 plus and 2 minus, then it's almost like when you're doing fractions, you know, what's the common denominator if you have 1/3 and 1/2? 1/6. So what I'm going to have to do is say, okay, I'm going to get to 6 positives and 6 negatives, and then it will be balanced. So to get 6 positives, how many aluminums do I need? 2. So I'm going to have Al with a subscript of 2. The subscript means I have 2 of those atoms. And to get to 6 oxygens, I need 3. So O3. And what do we call Al2O3?
Something. Try.
Okay, now that's good. I gave you a homework problem that's like this. It asks you, you know, what is it if you have like Ba2F? I don't remember what the formula was. But you only use the prefixes if there's more than one compound that has the same atoms. And in this case, there's no other compound with the same atoms. So, yeah, you don't know a priori. That's why I said that's good. You know, you're naming it using appropriate rules. In this case, there are no others, so you don't have to say dialuminum trioxide. It's just aluminum oxide. So the IUPAC name is aluminum oxide. And then you see other names for it like sintered ceramic, or if it's a single crystal, sapphire, or if you're into gemstones and it has lots of impurities, that's what they call sapphire. So aluminum oxide is formed, and here it's showing how the bonds are formed. See the dot structure on the aluminum? It has 3 electrons, 3 valent, right, because it's in column 13. Trivalent, I guess is what we call it. And then one of those is forming a bond with one of these oxygens. One's forming a bond with another. So notice there are 2 bonds between this aluminum and the oxygen. So we usually write that as a double bond to the O. So we write 2 dashes to say it's a double bond. The slide that I hope comes up next shows you the single bond is a single line. Then, so we have a single bond here, so a single line to an O, then a single one again, so a single bond to an Al, and then finally a double bond to an O. And so that's how the bonds are done. A double bond means we have 2 electrons that are being shared, not just one. Well, 2 pairs, because they're coupling up. And there's a second L, I forgot. So that's how it's formed, and just here's some pictures. Here's ruby. Ruby is Al2O3 colon chromium. Chromium is Cr, isn't it? Yes. So it has chromium impurities that give it that red color. And sapphire, if it's pure sapphire, it's just as clear as glass. I did research on sapphire. And that's just plain Al2O3 for the sapphire. And if you see sapphire that is like the gemstone sapphire, it has impurities to give it colors like green or blue. Cobalt gives it blue. Green, I think, is from an iron impurity. But it's impurities that give them the colors for the gemstones. Good to know, right? Why does the impurity give it those colors? We've actually already learned that. Remember when I brought out the gas tubes, we looked at them with the glasses and it was all Marvy and cool? That's because you have energy gaps between electrons. Well, the chromium impurity has an energy gap that will absorb light of the right color to make it look red. And so it's the absorption of electrons as they are being absorbed by those impurities that gives it the colors. Metallic bonds. Apparently I completely cut out that slide. My mistake. Maybe I was just hungry. I did it when I should have been eating supper. Metallic bonds are an interesting beast. Remember I said we're pretty much ignoring that section between column 2 and 13 because those are the transition metals. And those transition metals all have very weakly outer electrons, very weakly bound. And so those electrons actually travel through the metal. And because they travel through the metal, they give the metal unique properties, like it conducts electricity because the electrons are pretty free to move. And also conducts heat well because they're free to move. But one of the things that's cool about metals that doesn't apply to other things is they're actually held together by those electrons that are moving around pretty freely. They're not held together by bonds between atoms. It's the entire thing is holding it together. Almost in the same sense the way gravity holds the Earth together. The Earth is not held together by individual bonds between molecules and atoms. It's held together by gravity. Metals are held together by those electrons that are orbiting around. The nuclei are essentially positive charge, the electrons are negative charge, and they held it together. But you can replace a metal with another metal, and it doesn't matter. So we call that process alloying. You make an alloy by putting in different types of metals. And because the metal is not an atom-to-atom bond, it doesn't really make a problem. So you can make all kinds of unique alloys. And an example of alloys is something like, well, steel. Steel is an alloy of iron. It's mostly iron, but you have a few impurities, things like carbon This here is a picture of a Sacagawea dollar. And the Sacagawea dollar has manganese brass, and this is the recipe for that manganese brass and alloy. Brasses are alloys of copper and zinc. So manganese brass is going to have some manganese thrown in there. And in this case, it has a little nickel as well. And you get the pretty color because of the copper, I believe. And the metal properties, putting in different atoms will actually change the metal properties. And you can look up and find a lot more, but you can only alloy metals because of the way they're held together. Oh, here's finally the picture. Hey, it's still there. I just put a few things in between. So here, for a fluorine bond, if you do the dot picture, you had this electron here goes with this atom. And this electron here goes with this atom. And so you have an electron that, two electrons really, that are shared between the atoms. Each atom is contributing one electron to be shared with the other. But by sharing, each one can kind of pretend that it has the right number of electrons in its shell, it's complete, and it makes it more stable. This picture here actually doesn't show reality any better. But we do have a picture with hydrogen that does show reality better. So we draw the single bond with just a single line between. So when we're sharing the two electrons, that shared two electrons we draw with a single bond. Now when we saw the aluminum we had an O that was sharing these electrons and these electrons. That's how the double bond was working. And then it was it went on like that, but that's how the bonds were working there for the double bond. It was sharing this one and that one. So it goes on. I only showed one piece. I already went through the water one because I want us to have some understanding of what that picture was showing. So the water, we have two lone pairs. Each hydrogen attaches to a lone pair. And then we have charge shared between the two, but not necessarily shared equally. Just another example, ammonia, NH3, has a nitrogen that has 3 electrons to share. Each hydrogen attaches to one of those. And finally, methane gas. Methane carbon has 4 to share. Each hydrogen, if it attaches to one, you have a carbon with 4 hydrogens. If you were going to use the naming structure we've used, you would call this carbon tetrahydride. But it has the common name of methane. And with carbon and hydrogen, you have lots and lots of different variations you can have. You can have 2 carbons and 6 hydrogens, or you can have 2 carbons and 4 hydrogens, different ways of putting them together. So here are just a couple pictures. Oxygen. Oxygen is O2. You have an electron shared from one oxygen to the other oxygen here in the O2. And so each one is forming a double bond. So when you draw the bond, that's an electron from one and an electron from the other. And so you count that bond as 2 for each atom. So I have 2, 4, 6, 8 to get me the total complete outer shell. And of course, here's carbon double bonded to 2 oxygens. Here's nitrogen with a triple bond. If you were to draw the picture with the dot picture, you'd actually put Actually, nitrogen doesn't have that. Yeah, it does. And then you have a bond formed here, a bond formed here, and a bond formed there. Here's showing how the electrons are actually shared. So that's an H2 bond, hydrogen bonded to another hydrogen. The electron is shared between the two. At any moment in time, the electron could be with the left hydrogen or the right hydrogen. You don't have a way of differentiating one electron from another. You can't say, oh, this electron belongs to the left hydrogen, this one belongs to the right hydrogen. And so all we can do is say we have negative charge that's spread between the atoms and shared between the atoms. So there we have a hydrogen atom shown with the way the charge is spread. If we change it from a fluorine or to a fluorine, so it's an H and an F, the fluorine really wants electrons. We call that the electronegativity, is how much it wants an electron. The fluorine really wants an electron, the hydrogen not so much. So the fluorine basically pulls the electron spends a lot more time around the fluorine than it does around the hydrogen because the fluorine was greedy. So we call this the electronegativity, the pulling power for electrons. And if we look at the periodic table, the lowest electronegativities are bottom left, francium 0.7. That's a measurement of how much it's trying to pull an electron to it. If we come up here to the top right, fluorine 3.98. So if we had something like francium and fluorine come together, can they form a bond? Yes, because fluorine has 7 valence, it wants one more. Francium has 1 valence, it's willing to give one up. And that electron is just going to transfer over. The fluorine's pretty much going to own the electron, and then you're going to have a positive and negative bound together. What do we call it when they were bound together because one's positive and one's negative? Ionic. So it formed an ionic bond. So you have the two bonds we've talked about, ionic and covalent. Now this has covalent broken into two pieces, nonpolar and polar. A nonpolar covalent bond is a bond where the electron is shared equally between the two atoms. When we talk naively about covalent, that's what we usually say. Covalent means the electron shared. We assume equally. But often they're not. If you have something like hydrogen and fluorine, the fluorine wants the electron more than hydrogen, and so the electron spends more time with the fluorine, so you have a net negative on this side and a net positive on that side, but it's not so big. If you take sodium and fluorine, then it's a much bigger separation. It's interesting how the colors don't correspond with the electron charge, right? This side here was light blue for positive, this was light blue for negative. But you have different amounts of the electron held. How do you know the difference? You look at the electronegativity. If the difference between electronegativities is 2, it's going to be an ionic bond. If it's between 1.6 and 0.5, it'll be a polar covalent. Less than 0.5, we call it a nonpolar covalent. And anyone with any sense of curiosity is wondering why those two numbers are not the same. And the reason is because metals and non-metals are treated differently. So if it's a metal, then it's going to be ionic, I think, all the way down to 1.6. If it's not non-metal, it's going to be polar covalent up to 2. Okay, ending on molecular polarity. If I have a straight atom, carbon dioxide, if it's straight, even though my bonds between carbon and oxygen are going to be slightly polar, how do I know how polar? I look here and I say oxygen is 3.44, carbon is 2.55. 3.44 minus 2.55 is equal to 0.09, right? And so that not 0.09. Good math, because 3 minus 2 is totally, was that 0.89 then? Yeah, 0.89. So 0.89 puts it clearly in this realm. So they're polar covalent, but being polar covalent with both of them having negatives on the outside means that overall it's going to be nonpolar because the charge separation is uniform. Now, if we take water, and yes, I will end here on water, because it's not flat, it's not symmetrical. They're not opposite to each other, and so this is polar. You have a negative charge on the oxygen side, positive charge on the hydrogen side. Okay, we'll stop there. I'll see you on Wednesday.